Okay. So we have radians. Right? And then we want to get it per second. How often does it occur? So then we divide. Hold on. I messed up over here. I was looking at the wrong, sorry, I got confused. So here we want time. Right, and this is radians. Radians per second. Yes. So we have that. And then for the frequency, we want per second, we want 1/seconds. We want to see how many times does this occur per second. So we would want the omega, which is radians per second, over this, and then this will give us seconds. Right? 1/seconds. Right? And this is just a measure of how many times does it repeat itself in 1 second. And then we can see that the relationship between the period and the frequency is 1 over the other one. Right. So we'll use these two definitions over and over again, right? If I tell you the period, how long does it take to go around? You know that you can figure out the time it takes to move this much, and you can figure out omega from that. And or if I give you the frequency, you can figure out omega from that. And that's usually how it's done, is that it's easy to measure these quantities. How long does it take to move around, and or how long, how many times does it occur in a given amount of time? That's easy to measure. So usually you're not given the angular velocity. It's a more difficult quantity to measure. You're given the frequency and the radius, and then you have to figure out the what omega is. Okay, so now what's interesting is omega is a vector quantity. How do we describe omega, let's say, as a vector quantity? Right? Because if you think about the motion around the circle, it's always changing, right? So as it's rotating, the motion of each point is changing, right? So and we would want omega to be constant, right? We wanted to describe the general properties of something that's rotating. Can anybody think of a thing here as we're rotating that will stay constant? As it's rotating about this axis, what stays constant? I'll give you a hint. If this is rotating about a point, yes.
The radius?
The radius is constant, that's correct. But I'm talking about, well, the radius is constant. What else is constant? That's not a good one to well, if you think about it, this radius is constant, but it's always, this line that we draw for the radius, that's always moving around, right? That's always moving around. What's the only point on this circle that's never moving? There's actually one point on the circle that's not moving as it rotates, or this cylinder, whatever you want to call it. It's the center. The center doesn't move, right? The infinitesimally small center, it doesn't move because R is 0, right? If R is 0, there's no tangential velocity, right? There won't be any motion of the center. So to describe these vector quantities in circular motion, what we use is the vector perpendicular to the motion through the center. So we use the axis of rotation as the vector quantity. Now that's very, very strange, right? Because the objects are not moving in this perpendicular direction in and out of the board, right? And it seems like it's kind of arbitrarily chosen to be that way, right? It seems like it's just out of convenience, out of mathematical convenience, that we chose to describe the angular velocity in and out of the page. It doesn't make sense because the motion is in the plane. Why are we choosing this vector that points out of the plane to describe that motion, right? And that's very unintuitive. That's the most unintuitive part about angular motion, right? And I just described the reason why we do it because this point never really moves. The axis of rotation doesn't change, right? And it turns out that this is very good to use this type of perpendicular axes. And the physical world works quite well because of this perpendicular axis. And we get very interesting phenomena that occurs that wouldn't otherwise occur if we didn't use, in this case, the angular velocity as perpendicular to the rotational motion. Right? Now, and we'll see later on. And the way we describe this axis, whether it goes into or out of the page, whether it's positive or negative, this angular velocity, is by using something that's called the right-hand rule, right? So this is called the cross product, and I'll go into it. I'll describe it mathematically in the next chapter, but here it could be described as the right-hand rule, and this is a convention to describe the angular motion. Now, what we'll do is we need to define a perpendicular vector according to how we move. And what we call positive and negative is based on our right hand. So our finger, the direction that our fingers points, we put that towards the motion towards the circular motion. In this case, it's going upwards. You see my hand, how it's rotated around. We describe that as the circular motion, and the direction that my thumb points is the direction of omega. So here, omega points out of the board. And the way we write this down in 2 dimensions, if it's pointing out of the board, we draw a circle, we draw a dot with a circle around it. And the reason why we do this is for the sake of an arrow. So imagine the vector as an arrow, right? We have an arrow. If the arrow is pointing at us, all we see is the point. So that's why we draw the point, right? It's pointing out of the board. We're looking directly at the arrowhead. If it's into the board, we're looking at the back of the arrow, So we draw an X. So if it was rotated the opposite way, if it was going downwards now, my thumb would be pointing in the board. You see it? But it's going into the board. Right, you see it right here. Be going into the board. And this is how we figure out the direction of this angular velocity. Now we'll go into momentum in a little bit, but momentum, there'll be such a quantity as angular momentum, right? And I'll introduce this now. This is like the topic of the next chapter, but I'll introduce this now since we're on the topic, right? The angular momentum, which we'll call L, is given by this quantity I, which we'll go into, and the direction is omega. So the momentum associated with the motion of this is actually pointing out of the board. Now that we have a real quantity that you sort of intuitively understand as momentum or the inertia, how can the inertia be pointing out of the board when all the linear momentum is pointing in the plane, right? It's very unintuitive, right? How could we manifest this quantity L, or angular momentum, and have it manifest in and out of the page when all the linear momentum and everything that we intuitively understand about inertia and momentum is in the page? But what happens, you got to realize, is that this is a net quantity that depends on all the positions moving in concert. So if I have this point and this point moving in the same direction, right? If you look, these 2 points, if it's symmetric, the linear momentum cancels out with each other, right? Essentially. But because they're on opposite sides of a circle, what happens is that it's difficult when we rotate the circle. Imagine us rotating it around this plane like this, right? We'll be changing the momentum vectors of these points, right? As we rotate it, we're changing its momentum in this direction. And because of that, like let's say if we rotate it along this axis in the plane of the board, right? And we rotate it this way, right? We're changing the momentum vectors of any momentum component along this direction, right? And this would be, these 2 points would have the whole component pointing around there. And we're rotating it, we're changing the momentum vectors along here, right? And the fact that we have all the linear momentum of all these points, they manifest itself as if the angular momentum is out of the page, or the momentum that we would feel if we try to rotate a spinning disc, right? It would point. It would be hard for us to rotate it. We would feel it as a momentum pointing in and out of the page. So it's all these points working in concert. Well, this will lead to this net effect of the momentum, which is in the same direction as the angular motion, in and out of the board, right? And we'll come back to angular motion in the next chapter. I was just on this, so I wanted to talk about it now so you guys intuitively get some intuitive understanding. It takes some time. You really have to think about it yourself and work out all the little details yourself. You know, think about how it spins and come up with a scheme to have some intuitive understanding why these vectors would point in and out of the plane of rotation of motion. Okay. So that's these angular quantities, these vector nature vector nature of these angular quantities. Now, next we'll need the kinematic equations of motion for angular motion. We're not going to derive them because they're just an analog to linear. So for angular motion, it'll satisfy the same laws as long as the angular acceleration is constant. So we'll have omega is equal to omega naught plus the angular acceleration times time, right? Theta is just omega naught t plus 1/2 alpha t squared, same thing. Right, and this is always assuming a constant. This is a different definition of C. So this is a constant. That's a constant. So C over here is a constant, not the circumference. And then we'll get that. The omega squared is equal to omega squared naught, initial value, times alpha t. And then the average omega is just omega plus omega naught over 2. So we got the same, we work with these quantities in the same way. Right? Now go over the example problem, the example problems in 10.3, example 10.6, take a look at it. And it's pretty much a plug and chug. Just give you a problem and you have to calculate the angular acceleration based on its initial angular velocity, and its frequency. So frequency can be given in RPM, right? So frequency could be given in RPM, like in this problem 2.6, it's given as 20,000 RPM. What does RPM mean? Revolutions per minute. How many times does it rotate in 1 minute, right? So we'll have to convert this to how many times does it rotate in 1 second. You would divide this by 60 to get it, right? So the frequency would be divided by 60, and this is revolutions per second, RPS. You don't usually write it like this, but and this will give you the frequency. And this is per second, right? The number per second. And then from that, you have to calculate omega and whatnot. Okay. So the next thing to talk about is how do we describe force, right? I briefly talked about angular momentum because we were talking about angular velocity in these vector quantities, right? But how do we describe force, right? Now think about it. Think about how different it is when we describe about accelerating something in circular motion, right? So the best way to do this, and you can easily feel this in your own home, is by looking at a door. Right? Now, I introduced this in the lab. There's 2 people waiting. Sorry, I forgot to disable the waiting room. Those of you I just let you in. This is how we describe angular motion. It's basically an analog of the linear kinematic equations. We just replace the linear terms with the angular terms, and that's basically it. Now we're talking about something called torque. Right. Now torque is the analog of force with an angular motion, but it's a bit different. Right. Now imagine if we had this door, right? Go to the door in your house. Imagine if we pushed on the door over here, or let's say we provide a force into the board over here, right? How hard is it to push the door closed when you're close to the axes? It's much harder, right? The closer and closer you get, try to push on the door right next to the hinge. Try it right over here. It's really hard to close the door. It could take almost all your effort. Like if you're, it can take all your effort. A grown man, all his effort to close the door at this point, right? But at this point, a baby can open it. If a baby pushes on the door, at the edge of it, a baby can close the door, right? So where you apply the force on the door matters, right? And this is the key defining moment, the key separation between force and torque. And this is how we will relate torque force. Now, not only does it matter where you push on the door, right? What also matters is the direction that you push on the door, right? You got to realize that the door is constrained by the hinges to only do rotational motion. So what happens if you push on the door perpendicular? If you take the door and you push on it perpendicular to the hinges, what happens? It doesn't move, right? Because you're pushing on the door, you're providing a force. There's an equal and opposite force from the hinges itself, right? Like a normal force, you could say. And it doesn't move, right? So it also matters about the angle relative to the radius that you push on the door, right? So let's look at it. Let's look at a top-down view of this. So here are the hinges, all right? If I push on the door this way, if I provide a force this way, it's not going to move. Well, perpendicular, right? It's not going to move. And then, so what matters here is this. This is R. And then if I push on it this way, the only way that the hinge could provide a normal force is if it's perpendicular to the surface, right? And this is the only direction that it's perpendicular along R. So if I push this way, at this instant, this hinge can't provide any normal force to stop my force from pushing it forward, right? So what matters is this angle, theta from R, right? The angle compared to the axis of rotation, right? And now, this distance and the angle, this is called the lever arm. Where does this come from? Think of a lever. So I have a fulcrum, and let's say if I want to lift up an object, I create a lever, right? I have a heavy object over here, and I want to lift it up using my weight. right? I push down over here and I lift it up. And the reason why I lift it up is because of the torque, right? Even though this box may be much heavier than the force that I apply, the fact that it's closer to the axis of rotation on the fulcrum, my force counts more in terms of torque than the box does. And this is called the lever arm, because this is really where it was first developed, was for levers to lift heavy objects. And I think it was Archimedes. He said, one of the agents said, if I had a lever large enough, I could lift up the earth. And he's right, because if it's long enough, you can keep increasing R until the force that you apply equals or the torque that you apply with your limited force will lift up the object, right? So if you had a lever large enough, you could lift up the earth. And he was right. But the thing is that you need a fulcrum large enough and something to support its weight, which is obviously impossible. So this is called the lever arm, right? How much of this force is perpendicular to the axis and proportional to R, right? So let me draw it a little bit differently. Okay, so let's say in general we apply a force like this. This is the force. This is R. Right? In general, it's this component that really counts here. So we draw it. This makes a right angle. And we call this the line of action. This is on figure 1013 on page 256. We have the line of action, and really, this is the effect of R because of our angle, right? Because of our angle, our force gets limited to this length for R, right? If we were perfectly perpendicular, it would be the full length R. Because of the angle, really, we increase the force, the torque, by this much. And we've talked about this, but I didn't write down the equation. And this is also known as R perpendicular. So in the end, the torque, which we'll describe by this symbol, tau, is equal to this R perpendicular times F. And we just use trig to convert this into the radius, since that's easier to work with, and the angle. And this is sine because it's the opposite. This R perpendicular is the opposite leg from theta. So this would be RF sine theta. And this is the magnitude of the torque. All right. Now the torque is proportional to tau. Right? And we use proportional because there's an analog of mass here, right? And we call it the moment of, we'll go into it in a little bit, but let me introduce it. We call it the moment of inertia. So it would be given by this, the moment of inertia. Now, the moment of inertia is like mass, but it takes into account the distance of the mass to the center of the rotation. So the mass over here counts more than the mass closer to the hinges. A very similar intuitive understanding as the force, right? The mass counts more, creates more inertia the farther it is from the center of rotation, right? It's moving the tangential velocity is faster, so the linear momentum is faster. It counts more, and we'll go into describing that. I think we did it. So, and the way we'll calculate it is very similar to how we did the center of the mass calculation before in chapter 9. All right, so. So this is torque, right? We have to take for this angular acceleration. We have to take into account the radius that we apply this force to, and the angle to the axis of rotation that we apply this force to, right? Because usually when it's rotating, you only angularly increase the velocity if there's a portion of the force perpendicular to R. Right? Now, please go over example 10.7 at home. If you have any questions further on this topic, don't hesitate to email. And if you feel comfortable, you can include the rest of the class in the email, and we can have an open discussion. Problem 10.7, example 10.7 is pretty simple. So I'm going to skip it, and we'll go to rotational dynamics. So. So here, let's consider, and here we'll describe the moment of inertia. So let's consider a single particle. Right? That's the center, and it makes circular motion around here. Right? This is R. And then we have a force. Right? Okay. So now, let's say we provide a force this way, right? F is equal to ma of this particle, right? This is a point particle, it's very small, right? And in terms of angular acceleration, right, we convert A into alpha, and we get this, right? The tangential acceleration, I'll write it as tangential because it's along here. The tangential acceleration is equal to this. Can't really read that quite well. Okay, right? That's equal to R times alpha, right? then if we want to get the torque is just equal to, in this case, because the angle, this is 90 degrees, right? This is a right angle. So then from our equation before, where we have this, right? Where we have this, sine theta is 1, so we'll have R times F, and then we'll plug in what we have for F, and we'll get mR squared alpha. And if you look at this, it's the torque times mR squared alpha, right? This looks very similar to what I said earlier, where I said the torque is equal to this thing that we call moment of inertia, very weird term, times alpha. And if we look at the two, we can determine that we'll use this to get moment of inertia. So this would be the moment of inertia of a single particle. And it's a little strange because instead of dependent on proportional to R, it's proportional to R squared. And in general, let's say if we had a solid disk and we wanted to find the torque on this disk, like let's say if this is a solid disk and we wanted to find the torque due to the force, due to this force, we have to sum up, we break the disk up into infinitesimally small pieces like we've done in many times past, and we sum that all up. So the sum of the torques, right, is equal to the sum of all the masses and the positions of each mass times alpha, right? So the sum of each, the sum of all the torques, right? Remember, realize that this is just Newton's second law, right? The sum of all the torques, or the sum of all the forces, is equal to the angular acceleration or the linear acceleration, respectively, right? So the sum of all the torques is equal to the sum of all the moment of inertias plus times the alpha. Remember, this is a rigid body, so each point experiences the same alpha. We're allowed to say this. So in general, I is equal to this, where the masses are weighted by the distance from the center squared. So the distance from the center counts twice here. All right? Any questions on this so far? Don't hesitate to ask anything. This is probably the hardest conceptual part of the course, to be honest with you. Anything I can make clear? Anybody? Okay. If you have a question, don't hesitate to ask or interrupt me. It's okay.